Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone. We were talking about discrete random variables and specifically expectation. So as is clear, we didn't finish discrete random variables in a week, but actually a lot of what I'll cover will be relevant to discrete and continuous, including the definition. But there's an issue about that because, okay, so here I've got theorem, this is from last time. Here I've got theorems about expectation. And the definition of expectation left something to be desired. Does anyone remember? Well, I only did a very restricted definition of expectation. No, maybe that's not good. Okay, which kind of random variables did I define expectation for? I haven't done it for all random variables. Discrete, definitely, but there's actually more restriction than that. Okay, by the way, the formula is the same regardless, pretty much, but I only really confidently defined it in the case where it was discrete and had, anyone? Let's get back to the page. Well, independence is for multiple variables, but we're talking about this one variable. What was the extra restriction? Finitely many values. So just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, n. So not even countably many. It's finitely many. Why did we do that? Well, if I do that, there's absolutely no, it's totally unimpeachable to write this. So what I've defined of a random variable with finitely many values is something that always exists, and there's no question about it. And those theorems that we want to prove, in the first instance, I'm going to prove them for random variables with only finitely many values. Now, you'll think that that's a bit hopeless, but ultimately, it turns out everything else is essentially a limit of these. You know, you can approximate any random variable at all by random variables that only take finitely many values. It might just have to be a large number of values. So ultimately, once we've proved it for finitely many values, we will be able to go on and do it. So let's concentrate on our theorem. Our theorems. Firstly, expected value of a constant is a constant. Maybe I don't need to spend some time on some of these, but I do want to prove some of them. By the way, I actually phrased let's go back to the definition. I phrased it in two ways. Number one, you could have n values of the random variable, and then just write it this way. So pi times xi. Pi is the probability that x equals xi. Or I wrote it with indicator functions, which seemed a little obscure to some, perhaps. Strange thing to do. But, of course, EI there could just be set to be the event that x takes the value xi. Remember, 1 is a function that is 1 on the event that EI and 0 otherwise. So this funny sum is a special random variable that will it will be xi exactly on the event EI. So if EI is the event that you want xi, it's kind of sort of logically what you want. This is actually more general. For instance, when you're just setting EI is x equals xi, then they don't overlap. But this formula is true even if they do overlap. Now, you might say, how is it okay for a definition to be okay if they overlap? Well, if you phrase it in this way, you sort of need to check that when you break an event into two events, you get xi times probability of the first part and xi times probability of the second part. So you have to check consistency. But it is true, it follows from the axioms of probability that this is consistent. Okay, so I'll just let that go without saying it. It's very easy to check that as a reinterpretation. But this is actually a bit more powerful, especially when we're doing the proof. So let's now prove this theorem. Once again, only in the context of random variables that take finitely many values. So that's in particular discrete, but even better than that. So proof of theorem for random variables x and y that take only finitely many values. So discrete plus even a little bit better than discrete. Okay? But still kind of easy to do. So okay, well, C is a constant. That only these ones automatically take only finitely many values. I'm just going to say 1 and 2 are, they're from the definition. You can just check that this is exactly what the definition says. If you're a constant on the whole, that would be, effectively this is C times indicator of omega, indicator of the whole sample space. And this is just, yeah, so it's straight from the definition. 3, okay, this might be a little bit harder, but not too hard. We're always allowed to write x is sum of xi indicator ei for some events. Right? And this will be finitely many. Okay? That's the whole point about a variable with finitely many values. And then, so, the C times x is a random variable. Once again, it's the random variable whose value is C times xi on the event ei. Right? You just multiply it by C regardless of where it happens. So if you don't like thinking of it this way, you can imagine that the EIs are disjoint events, and then just imagine that it's described in the old-fashioned way as, you know, equals x1 with probability p1 equals xn with probability pn. That would be another way of saying it. But I just prefer to write it this way because it makes the proofs very easy. Expectation of, see it, you know, very easy. We're just going through that rephrase in case you want a reminder of what that rephrase definition was. Using this rephrase definition, all you have to do is the constant times the probability of the event. Okay? Which is, and then I can take the constant out the front. Okay. And that is really constant times the expected value of x. So that's really using this definition that I've called star here. Okay, so let's do 4. So it's 3 was the easy one. That's the warm-up. Now we're going to do 4 and 5 by the same. Okay, now you might have forgotten what 1, 2, 3, 4, 5 was. So I'm now going to pull them down a bit. Okay, so to do 4, we now have to do. We'll just do the case expected value of x plus y. Was expected x plus expected y. We have to prove this. Why is it enough to do the plus code? Well, okay. It turns out it's because we've just done number 3. Number 3 says if you want to negate a random variable, the expectation also gets negated. You could take c equals minus 1 in example 3. That would tell you that expected value of minus x is minus expected value of x. So to add, you know, to do x minus y, you'll just do x plus z, where z is minus 1. So adding and subtracting are the same thing, so long as you know how to multiply by minus 1, which we do because of chapter 3. So we'll just do this case. Now, how do we do that case? Right. Okay, what we're allowed to write is x is sum I equals 1 to n of xi probability of, xi indicator on event ei. And y can also be written, but the key thing is that y might have different events. So y, j, and these might be other. So, and I'll even say m instead of n. So y might have a different number of values, a different number of events, and different values. So I can't a priori. So these are for some xi's, yj's are real numbers, of course, and events to have the EIs and FJs all have to be events. So you don't know that they're the same. So then, x plus y is equal to sum I equals 1 to n, xi over e, plus sum equals 1 to n, yj indicated fj. Okay, so that's what it is. So, so it almost follows straight away. So you see that this rephrasement is a kind of very trickily clever thing that because you relax it so that the events are allowed to overlap or not, it doesn't matter. Now we're going to apply it where the events overlap. The EIs might overlap with the FJs, and it doesn't matter because the phrasing star is still true. So expected value of x plus y is equal to expected value of this stuff above. So the rule is you just take up x sum of xi probability of ei plus sum of yj probability of fj of the indices are the same of summation. So that equals expected value of x by definition plus expected value of y. So it seems almost nothing. And I'm just going to do number 5 because that's the one where it starts to get interesting. The product. And there's a condition on being able to multiply expectations for expectation of xy. That condition that's not present for adding. Someone say? So we're all on the same page. To do expectation of x times y is expectation of x times expectation of y. You have to know that they're independent. Because if they're not independent, many things can go wrong. For instance, you know, if it's just an indicator variable, then the expectation of x is the probability of it happening. So expectation of a Bernoulli is p, but then if you put x and x, you would get p squared. So p is not equal to p squared. There's all sorts of things that can go wrong if they're not independent. So the only case this is true is where x and y are independent random variables. Okay, so let's continue with the proof of 5. Now, by the way, it's not a proof-based course, but since this is such a fundamental theorem for everything going on, I think it's important for me to actually give this. So once again, we're going to write, as before, the same x can always be written as sum I equals 1 to n of xi indicator ei, and y is sum j equals 1 to n yj indicator fj. Once again, to reiterate, the events for x don't have to be anything to do with the events for y. They can be totally unrelated random variables. And then xy is equal to, I'm just going to write it out, product of the two sums. So full expansion of that would get n m terms. I equals 1 to n, j equals 1 to m. And then the corresponding term is obtained by multiplying those two together. xi, yj, indicator ei, indicator fj. Now, can anyone thinking about indicator variables tell me what happens when you multiply the indicators of two different events? It's still a variable that's only 1 at certain times and only 0 at other times because you're multiplying zeros and ones together. So it's still a 0, 1 random variable. It's still an indicator of something. What is it the indicator of? I'm multiplying it. Of the intersection, thanks for saying that. Yep, because for the product to be 1, both of them have to be 1. So you have to be in both EI and FJ. That's an AND, which is an intersection. EI intersect FJ. Okay? So the expected value of xy, once again, we're using star. This little rephrasing sort of makes, I did it because it makes the proofs it almost seems like they're over before anything happened. So sum I equals 1 to n, sum j equals 1 to m, x, I, y, j, and then I have to, that's the constant out the front, x, I, y, j, and I also have to multiply by the probability of the corresponding events, probability of E, I, intersect F, J. Okay. So implicitly here, EI, just in case you're wondering where on earth these events came from, EI is just the event that x equals xi. There's nothing going on there. And fj is just the event that y equals yj. Because there's only, you might be wondering why can I write it as such a sum? It's because we're still restricting. I'll remind you for this proof of the theorem, there is a very important restriction for random variables that take only finitely many values. So that's not fully general yet. Because they take only finitely many values, I can write it as a finite sum with indicator variables. So it's xi, it's sort of logical. It's xi when it equals xi, it's xj when it equals xj. You know, y equals yj when it equals yj. So that can be written, and you go on like this, and the key step that we're using, our key fact that we had to assume was that x is independent of y. We have to use that, and we're going to use that at this step. Can anyone suggest, while I'm writing this down, what the appropriate way to use that is? The constants will stay the same, x, I, y, j. What is the probability of EI intersect FJ? You just have to remember what is EI as an event. EI is nothing other than the event that x takes a particular value. By the way, can anyone remember the definition of independent random variables as opposed to independent events? Independent events are those whose probabilities multiply to get the intersection. Independent random variables covered that last time. Anyway, it means that any interval, you might ask x to be in any interval, and you might ask y to be in any interval, and those are corresponding events. Those events must always be independent, regardless of which intervals you pick. So one interval, you could ask for x to be equal to xi. A single point is an interval. Interval is just more general because it allows for continuous as well. But yeah, you could just ask for x to be in xi. So EI is one event that x is in a particular interval, and fj is another event that y is in another interval. Those must be independent because the x and y variables are independent. So therefore, I'm allowed to replace this by exactly times probability of fj. So the logic is like this. By the way, random variables being independent is a big beefed up version of events independent, because if you say random variables are independent, there's a whole family of events on the x side that are independent of a whole family of events. So it's beefed up. So we're using that in a particular context where EI is independent of fj. That follows. Yeah. Okay, so probability of EI times probability of fj. So now it's a moment for those of you who like algebra. Any suggestions? To get the ideas flowing, I'm going to put all the i's together, because I is sort of on the x side and j is sort of on the y side. Okay? So all of this part is sort of depends only on which index I you chose. And all of this part only depends on which index j you chose. Is anyone familiar with seeing those kind of product? If you have a double sum where you have something of the first sum times something of the second sum. It's a product. This is what you would get if you expanded out the sum on the left times the sum on the right and just put every pair. So for every pair of I and j, so there are nm pairs. Each pair consists of picking one I and one j. And the I gives you this term, the j gives you that term, and they're multiplied together. So it's exactly the expansion of this product, this sum. I equals 1 to n xi probability bi. Sum j equals 1 to n yj probability of j. So that's pure algebra. Finite sum. Each sum has an I component, a j component, and you add all nm possibilities. Okay, and lo and behold, you go back to our, in case anyone forgot, this is the rephrased definition of what the expectation is. The expectation of x times the expectation of y. Okay, so that's the end of the proof. We've proved everything now, and only in the fifth one did we require them to be independent. Now, I don't want to say that the proofs are the most important thing, but I do think it's important that things don't become a whole wave of assertions, because you might, there's sort of barely any, otherwise I might just give you some sample wisdom that you don't know where it came from at a totally different level. So let's continue. The defect is we haven't defined all random variables. So we're going to now define the expectation for all random variables. And unlike ones that have finitely many values, when you're talking about all random variables, there's a possibility the expectation might not exist. Okay, it's a bit strange, but I'm just warning you about that now. And why could the expectation fail to exist? Well, there's any number of reasons, but and if you think back to, let's go back to this concept of expected value of a random variable x. If you go back to the concept, it's the long-run average of many independent and identically distributed trials, each of which has the same distribution of x. Now, what if there were no long-run average? It's kind of funny. It turns out, for certain variables, there will be a long-run average, for certain there won't. And let me give you there are many examples, but you might not be familiar with them. So the first one I'll think of is, if you spin a needle, this is a famous thing, Buffon's needle problem is if you spin a needle at a random angle and let it drop on a wooden board floor where the distance between the boards is the same as the length of the tile, then what is the chance that it hits? Anyway, just think of the first part of that, spinning a needle and letting it land at a random angle. And then, what is the tangent of that angle? Remember, tan of the angle can be quite high, because if you had like 80 degrees, it's really the slope. If the angle is near 90 degrees, then the slope will be very, very high. So the tan can be very high. It can also be very low. And if you you can even try this at home, or probably better is to program it on a computer and keep doing it many, many times. You'll find you spin this needle and you keep writing down the tangent of the angle. You will not get a long-run average. It's not possible. Because what will happen, I haven't used the computer that much. Let's have a little break. And, well, it's not a break because I'm showing you something. I'm going to show you that exact experiment in R. Now, R is not examinable, of course, but it can be useful for this kind of thing. So can you see this? Yeah. Let's do... so I'm going to I'm spinning an angle. Implicitly is every angle is equally likely. It's sort of uniform in angle. So let's just take R unif. By the way, I forget exactly what unif means, but I'm just going to, rather than look up the documentation, I'm just going to take 100 random uniforms, and I think it should be 0 to 1. Yeah, it's 0 to 1. So what I want is, instead of random uniform 0 to 1, I want them random 0 to 2 pi. So R unif 100, and then I'm going to multiply each of them by 2 pi. And so they're my random angles. So now, and let's make it 10,000, whatever. Okay, it's very easy for it to do many, and then we can see what happens in the long run. Let's do the tan. I just said tan of the angle, that's all. So I'm going to do tan of this, because the uniforms are not that interesting. They're just uniform on the angle. So that's going to be t is my vector of tangent. So I don't want to shock you, so I'll start by histing t1 to 10. So this just gives me the first 10. Okay, so there's a few tangents around 0, you get a -8, but nothing too. Where let's try 1 to 20. Okay, now we've got something near 20. That's kind of weird. Now I've got 1 to 30. I already did that. 1 to 50. Okay. I get 100. Okay, somehow I got a -400. That's a bit weird. Let's start asking about the mean of, yeah. So, because this is funny. If I just did it up to 50, my mean was, right, so you thought, until you got to 50, you think, oh yeah, we're doing some kind of normal thing. We're going to the mean is going to tend to 0, and all of a sudden you got a mean that was -6. So I bet by doing 100, I'm going to be around -4. So that -4 will wash out. Like if I have 200, it's diluted as much. So I expect to get about -2 and a bit here. Oh, but it's added another weird thing. So yeah, so that's more like what I expect. I doubled the length, and I expect to halve the mean, because the extreme values get washed out. That is, until you get another extreme value. So let's do it again. So it's suddenly on the other side. It's not so different, but 1600. So it almost looks like it's settling back to 0 again. But this would be misleading. See, it looked like it was kind of settling to 0. Now it gets to -1 again. Let's see. I think I've got a million to play with. So I just want you to... You might be thinking, oh, yeah, it's still settling down. Remember what I said. This is all about long-run averages. You keep doing it for more and more trials, and what is the long run? It's important that I'm using the same trial. I'm keeping the first 10 in it, and then I'm adding more. So how does it settle down? Let's... okay, I'll just switch to 10,000 now. Yeah, okay, exactly. I went barely from 6,400 to 10,000, and all of a sudden the mean is at -36. So not only do you... Let's go back to the hist of these guys. There was something very, very negative that occurred there. -3 to the times 10 to the power 5. So about -300,000. That was... Okay, let's find exactly what that mean value was. So the longer you go, the more you get. And it's as the number of trials increases, the outliers, if you might call them, maybe that's a bad word, but the extreme values get more and more extreme at a faster rate than can be compensated for by dividing by n. So this is a classic thing that does not have a mean. Now I just want to, if I, oh not mean, let's do mean. I reckon the mean should eventually go positive again. A fact about this, it actually goes as big positive and as big negative as you like, repeatedly. It zigzags between one and the other, so it's truly weird. So, okay, well, it's strange that the, okay, that doesn't exist. I went too far. So, okay, you would have to sample some more, but I guarantee you ultimately in the wash that very, very negative mean would actually have been, eventually become positive again. Okay. It's a long way of saying this variable has no, so let's do hist of the whole t just so you can see. Yeah, so oh no, there was an even worse one, -6. You thought we got a -300,000, that was extreme, and then there was a -600,000. And there was also a 400,000. So those are kind of surprisingly common. Needless to say, this is nowhere near normal. That's a first very good example of a variable that doesn't have an expectation and it has no long-run average. So let's get back to the theory of it, so having motivated it. And it's not a matter of discrete or continuous. Not a matter of discrete or continuous. This could, it's really about how likely large deviations are. Okay, so now let's, I do need to give you a definition of expected value of x for arbitrary, okay, random variables. Okay. So asterisk may not exist. Okay, so if you take nothing else from that little demonstration, the asterisk may not exist. Okay. So first, there's a first step, which is that if x is a non-negative random variable, okay. So that's either, you know, it's greater than or equal to 0 for all, or at least on a set of probability 1. So it's just, there's no chance that it's negative. Okay, then we define expected value of x is equal to, so, and this is totally general, this is not just discrete. So this is kind of more general than is needed for the course. I'll get down to what it means for discrete random variables in just 1 second. But it is the, okay, I would use the word supremum, but that's not an assumed knowledge for this course. So I'll just say it is limit as y goes up to x of expected value of y. Now what does it mean it goes up to x? First of all, I can't, this looks very self-referential to define expectation in terms of expectation. It's not self-referential so long as we already know how to do these ones. And the ones we know how to do are the ones that take finitely many values. So this is a limit taken over all random variables y taking finitely many values. Okay. Such that it has to be y going up to x. The meaning of the up to x is that y can, do anything it likes so long as it is below x, such that y is less than or equal to x. So i.e., y of omega is less than or equal to x of omega for... So that's what it means for one random variable to be less than or equal to the other. It means it's always true, or almost always true, for all omega. Sometimes people say almost all, which is a way of saying I don't mind if it fails on a set of probability 0, because sets of probability 0 don't matter. But we'll just say all. It's the same definition. Okay, so that's a definition of expectation of x for things greater than or equal to 0. But I just want to say this could be infinity. Okay? Because if you're taking an unbounded limit of things like for instance, just for the positive angles we talk about over there, the expectation would be infinity. You would get as large as you like for this expectation. So this is the definition, and this is what it is for absolutely arbitrary random variables. So soon we'll be much more specific to discrete. Okay, and second, I didn't talk about not variables that are not non-negative random variables. If x can take positive and negative random variables, we just write x. You can always write, x could be positive or negative. You just put the positive parts on one side and the negative parts on another. It's pretty easy. So y minus z, where y is greater than or equal to 0 and z is greater than or equal to 0. And you do that in a kind of minimal way, like just all the outcomes where it's positive, you make y positive and z 0. And all the outcomes where x is negative, you just make y 0 and z positive. So it's easy to do this. This is y is the positive part. So it's just called the positive part of x, and z equals negative part of x. It's literally, when x is positive, then it's y. And when x is negative, then it's minus z. That's all that means. Oh, yeah, sorry about that. Okay, so, and the definition is expected value of x is expected value of y. It's exactly what you'd expect. It's got to be linear minus expected value of z if these both exist. Now that's the trick. Expected both exist and are less than infinity. Okay, so expectation of y has to be less than infinity. Expectation of z has to be less than infinity, because there's no point trying to subtract something from infinity or take a number minus infinity. So especially, the worst one is you definitely can't do infinity minus infinity. That doesn't mean anything. And that example I gave you, which is actually called the Cauchy random variable, we'll possibly talk about it later, that's a case where the positive part has expectation infinity and the negative part also has expectation infinity. Okay, so that is the full definition. The theorem, I'll just say it carries over in full by taking limits. And you might wonder, how can that theorem carry over in full? Because it's saying something about expectations which might not exist. Well, it doesn't carry over in full if the expectation doesn't exist. Because, so, wherever that statement was. Okay, by taking limits. So, if expectation, you're talking about two variables x and y, and expectation y exists. Okay? Okay? So in terms of the word exist, does the expectation exist? If this limit that you got was actually plus infinity, you would use the word that it doesn't exist. Or you can sometimes say it diverges to infinity. But when we say exist, we mean that we want it to be a finite. Okay. So the theorem carries over in full by taking limits. There's really nothing to it more than that. I'm really not pulling the wool over your eyes, because limit of a sum is sum of a limit so long as the limits exist. That kind of thing. So I'm not going to spend any more time on it than that. So while that's the totally general definition of Ex for arbitrary random variables, that includes mind-bogglingly numbers of variants that we don't want to take into account. So now we want the definition for arbitrary discrete, for all discrete random variables of Ex for all discrete random variables. Okay. So then x, so x has, the distribution of x is described by the probability mass function. Remember, this is called the PMF. The distribution of x. Okay, when I say x is described, I really mean the distribution of x is fully described by the probability mass function. And then the definition is expected value of... Now you might say this is redundant because I've already done it. So really what I'm doing is I'm translating that slightly abstract definition into what it means for all discrete random variables. Expectation of x is sum over all... and remember that for a probability mass function, it is only non-zero on some list of numbers, x1, x2, x3. That was the whole point of being discrete. There's only finitely or countably many variable values at which the probability mass function is non-zero. That's just sum over all those values of xi, probability of being xi, so long as the sum converges absolutely. Okay. Now this is a technical term. I'll say what it means. Converges absolutely means the absolute values that you, if you tried to sum up all the absolute values themselves, you would get finite. I.e., if I sum I equals 1 to infinity of the absolute value, I don't have to worry about, the probability is already positive, but the xi might fail to be positive. Xi, px of xi is infinity. Okay, and for that, so you can just take that as the definition. For those of you wondering why this is the same as the preceding definition, you just let y equals positive part of x as before, and z equals negative part of x. Okay, and we know that the expectation of y is the sum of xi. Let's put it this way: xi indicator that xi is positive. P x of xi. P x of xi. That's what the expectation of y is. Because y is 0 if x is negative, and it's 1 other. And then expectation of z is sum of minus xi on the indicator function that xi is negative. Let's move to 0. Px of xi. Okay. So I put this in square brackets. Those of you who don't care can ignore that. But if you're wondering why that's the same as before, the positive part is the ones where it's positive, the negative part is the one where it's negative, and when you put together the ones where it's positive and it's negative, that's just shorthand absolute value. So that's what the sum converging absolute means. So it's long past time for some examples, and the best first example, okay, we have to do, no, we've already done indicator variables, and we've even effectively done binomial variables. I should even have done it before the definition for arbitrary random variables. I probably should have done it there, because binomials only take finitely many values. So all we needed was that theorem to do finitely many. This is all I needed was that theorem. So we'll get, okay, because it's so compelling, I'll do geometric P, because this is directly an application of this definition. If n, we called it n1 before, is geometric P, the expected value of n1. Now, because this is always greater than 0, okay? If it's greater than 0, you don't need to check for absolute convergence. You just do the sum. The absolute convergence is only a worry if you have both positive and negative xi's. Otherwise, there's no possible problem. And I'll get back to that later. So expected value of n1, I just write down the sum, I equals 1 to infinity. Now the xi's are actually I in the case of geometric. And what is the probability? Pn1 of I, which we can sum I equals 1 to n, 1 to infinity, sorry, I. And what is someone remind me what's the probability of what's the probability of, well, okay, geometric in our convention always is 1 or greater. So what's the probability of being 1? Remember, a geometric, you're doing repeated Bernoulli trials, all independent. You stop at the first success. So what's the chance you stop immediately? P, that's the chance of success. Chance of waiting 1 and going is 1 minus P times P. Chance of waiting I minus 1 and then going on, you have to do 1 minus I minus 1 failures, each of which has probability 1 minus P times P. Now, this is a little bit more tricky than the sum. By the way, if I didn't have I there, I would just be checking that it's a proper random variable that it sums to 1. And that would be a simple series in, that would be a simple geometric series. This is not a geometric series because it has the I there. But nevertheless, there's a way to do this. In fact, there's many ways to do this. First thing is if you like differentiation, you might notice that this looks a lot like a derivative, nx to the n minus 1. So it's true, it's a fact about series actually that you can differentiate and integrate them term by term. In fact, I hope you learned that in your math course that's covered in the series. Well, and the asterisk is within the radius of convergence. The radius of convergence is 1. Within the radius of convergence, you're free to differentiate that in term by term. So let me just put in brackets over here. What this reminds us of, I'm just going to do x instead of 1 minus p. nx to the n minus 1. Right? It reminds us of this sum n equals 1 to infinity is nothing other than d by dx of, that's the derivative of x to the n, right? Sum n equals 1 to infinity. Nothing. This is true so long as absolute value of x is less than 1 because that's the radius of convergence. So I've just differentiated under the sum sign. And does anyone, okay, so now I've got rid of the n down there. Now this is a perfectly good geometric series. Does anyone remember what the sum is there? Yeah, you've got a 1 minus the common ratio, 1 minus x. But the first term is not actually 1 in this context. It's n equals 1 to infinity. So it's actually x over 1 minus x. Okay, so it's x over 1 minus x prime. Okay, so you can actually write x over 1 minus x as okay, so that is d by dx. You can do the differentiation with the quotient rule. Probably a nicer way to say it is that this is 1 over 1 minus x minus 1. That way I've got the x out of the numerator. So that is equal to the derivative of 1 over 1 minus x, which is actually 1 over 1 minus x squared. So that's the formula that I'm using here. Substituting that in this case, x is equal to 1 minus p, so 1 minus x is p. So this sum is actually 1 over p squared times p. So the expected value of a geometric p is 1 over p. Do you remember nothing else? So if I'm rolling dice with a probability 1/6 of getting a 6, which might be success, then I'd be waiting an average of 6 turns until the first 6. An average of 6 turns until the first 5. Average of 6 turns until the first 1. And if I'm flipping coins, how many turns am I waiting on average until the first head? 2. 1 over a half. Which includes the head. So on average you're doing tails and heads. So the average number of tails is only 1 less. Okay, so en1 equals 1 over 6. Okay, that's nice. So let's go on and do the expected value of some other ones. We already saw that expected value of a Bernoulli, is probability of the event P. Okay, so Bernoulli's are easy enough. So Bernoulli P. Okay, let's make it x1 as Bernoulli P. The expected value of x1 is P, of course. The binomial, which we called a capital K last time, this is a binomial NP. Capital K is sum of I equals 1, I equals 0, sorry. Actually, that might have been a typo last time because Bernoulli's, I take that back. There are n trials, so 1, 2, 3, 4, 5 up to n. So the trials go from 1 to n. See, here I am summing up the Bernoulli trials. There's two things to keep in mind. The possible values of k are anywhere between 0 and p. So for the probability mass function, you would be taking a sum from 0 to p, 0 to n. But the actual outcomes that you're summing up, there are n of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the definition. So the expected value of k is, this is really using our theorem, although you might just take it to be common sense. Using 4 from the theorem, this is the sum of the individual things I might like to do. Expected value of xi. Yeah. And what is expected value of xi? Xi is, remember we had Bernoulli trials 1, 2, 3, all independent IV Bernoulli P. That's the basis of all these basic discrete distributions. So what's the expectation of x2? Someone say out loud? Well, we've already done expectation of x1, and they're all identically distributed. So they all have expectation P. Yeah, I need people that speak out louder when I'm asking for contributions, otherwise I can't hear. Okay, NP. Okay, so that's the expectation of a binomial NP. Now this is so much better than, people might be tempted to write out something along the lines of I equals 0 to n. Remember, these are, if you just go based on it is true, expected of k is I times the probability of being I, which you have to do n choose I, p to the I, 1 minus p to the n minus I. So, n minus I. Okay. Okay. Now, it can be done easily enough. You have to do some algebra with the binomial coefficient. But it's certainly not something I would encourage. It's quite open. Or another way to do it is to, some kind of differentiation, once again, with the p to the I. But it's really not pleasant. So it's so much nicer to do this. So that's a moral, generally in probability problems, is the most obvious way may not be the simplest way. The most obvious way, the simplest way may actually rely on another conceptualization of the problem. We'll see that even more so with the hypergeometric. Before I do the hypergeometric, I'll just remark that the expected value of a negative binomial, if n is negative binomial, kp, the expected value of n, once again, it's the expected value. How do you decompose a negative binomial in the natural way? What are these k different things that I'm adding up? Someone remember? There's a word. They're k geometric, independent geometrics, because negative binomial, you're waiting for the k success. In independent trials, you wait for the first, that's a geometric, you do it k times. You add them up, they're all independent. So that is sum of the expected value of ni, I equals 1 to k, and that is k times, what is each one the expectation? 1 over p, because it's geometric. So the expected value of n is k over p. So if the binomial one is bad, that's at least a finite sum. The negative binomial would be awful, and that's an infinite sum. And the hypergeometric is also quite bad, unless you take it conceptually, which we will do. So we've run out of time. Next time we'll, although I talked about hypergeometric in the context of combinatorics, I'll properly define it as a probability distribution and do its mean and variance, and we'll talk about variance generally. And we have to cover Poisson, and apart from that, we're pretty much finished with discrete variables. So we'll finish probably tomorrow with discrete variables.